So, we're in the middle of constructing a grouped frequency distribution. We've decided what the class limits should be. Now we're going to go through and count how many of these numbers fall into each class. Now, there are ways of getting a computer to do this for you. But if we're going to do it by hand, we can just go through the list one at a time and make sure each number gets counted in the appropriate class. So let's try this. The first number is a 28, so that gets counted in that last class, 26 to 30. The second number is a 12, so it gets counted in the 11 to 15 class. Then the 15 that comes next is also in that class, and so is the 11. Then we have 16, and then another 15, then an 18, 3, 23, 6, 4, 11, 13, 20, 1, 21, 7, 12, 25, 2, 13, by the way, we're on that bottom row now, 8, 6, 18, 17, 14, 7, 16, 9, 12, 20, 14, 2, 7, 6, 13, 12, 8, 5, 2. So it looks like what we ended up with for our numbers are our frequencies are 5 plus 2 is 7 in the first class. Then 5 plus 4 is 9 for the second class. Then we have 5, 10, 13. Then we had 7, 3, and 1. So there's our frequencies, 7, 9, 13, 7, 3, and 1. And if you add those all up together, 7 plus 9 plus 13 plus 7 plus 3 plus 1, they add up to 40. So this was a list of 40 numbers. What about the boundaries? The lower limit of the first class is 1. What's the lower boundary? If you said 0.5, you are exactly right. What's the lower boundary of the second class? 5.5. And then 10.5, 15.5, 20.5, 25.5. Notice that just like the lower limits and the upper limits, the boundaries go up by 5 each time, because that's what we're using for the width. And what about the upper boundaries? What's the upper boundary of the first class? Well, it's the same as the lower boundary of the second class. It's 5.5. And then the rest of those upper boundaries, 10.5, 15.5, 20.5, 25.5, and what's the last one? 30.5. What about the cumulative frequencies? The first one would just be 7. But what's the second one? 7 plus 9, which is 16. And what comes next? Well, 7 plus 9, which is 16, plus 13 gives us 29. And then 29 plus 7 is 36. 36 plus 3 is 39. And 39 plus 1 is 40. What about the relative frequencies? I'm going to pull out my calculator for this. Remember, there were 40 total, 40 in all. So that's what I'm going to be dividing by each time. So 7 divided by 40 is 0.175. 9 divided by 40 is 0.225. 13 divided by 40 is 0.325, and so on. So that's how I get the relative frequencies. 0.175, 0.225, and so on. And here I've chosen to write them as decimals, but you could also decide to write them as percents. And then what about the midpoints? What's the midpoint of the first class? What's halfway between 1 and 5? Well, you might be able to see that right away. We got 1, 2, 3, 4, 5. The middle number is 3. But if you can't see it that way, you can take the 1 and the 5, add them together, which is 6, and divide by 2 to get 3. What about the next midpoint? What's halfway between 6 and 10? That would be 8. You can probably just see that, but you can also take 6 plus 10 and get 16. Divided by 2 is 8. The next midpoint is 13. And by the way, notice that the midpoints, just like the limits and the boundaries, go up by 5 each time. So once you find that first midpoint, you can add the width to that to get the next one, and the next, and the next. So 18, 23, and 28. Now here's what I'm calling a bad example of a frequency distribution. In this example, and I just made up these numbers, but pretend for the sake of the example that this shows frequencies of auto accidents among drivers of different age groups. Like they looked at different age groups of drivers and how many auto accidents involved drivers in that age range. So this is saying that they found 63 accidents where the driver involved was age 16 to 20. And 49 accidents involved drivers age 21 to 25. And 219 involved drivers age 26 to 64. Wow, look at all of those. That's the biggest group. So looks like those are the drivers that get into the most accidents. The drivers that get into the most accidents, the worst drivers are the ones aged 26 to 64, right? Yeah, the problem here is that's a really wide class. 26 to 64 covers a very wide interval compared to just 16 to 20 or 21 to 25. So that's not really a good frequency distribution. We want all the classes to be the same width. If this goes 16, 17, 18, 19, 20, and this goes 21, 22, 23, 24, 25, then the next one really ought to go to 26, 27, 28, 29, 30 and stop there. And then we got 31 to 35 and so on. So let's say we do that. We go back and regroup things like that. And it does keep on going past this one, but I just showed you the first few classes. So now there's 63 accidents involving drivers age 16 to 20, 49 involving drivers age 21 to 25, 41 involving drivers age 26 to 30, and so on. Better, right? So now it looks like the 16 to 20-year-olds are the worst drivers. They get into the most accidents. 36 to 40-year-olds are the best, at least of the ones showing here. So that's a lot better. But there's still something you got to watch out for. Let me add a couple more classes at the beginning. So there were 0 accidents involving drivers age 6 to 10. and 8 accidents involving drivers age 11 to 15. And this tells us that these drivers are really safe. They never get into accidents. If you want to be safe, find a 6 or 10-year-old to drive you somewhere because they never get into accidents. They're really safe drivers, right? Yeah, it's not that they're such safe drivers, it's that there really aren't that many drivers at all, age 6 to 10, or even 11 to 15, although you might have some 15-year-olds with like a learner's permit. So we got to keep in mind what we're looking at here. And the fact that there are 63 accidents involving drivers age 16 to 20, it might mean that they're worse drivers. Probably does. They're young and inexperienced. But it could also mean that there are more drivers in that age range than in others, or that they do more driving than drivers in other age ranges. That's probably what's not what's going on here, but it could be. So, a good frequency distribution. For a frequency distribution to be correctly constructed, there are some things that ought to be true about it. You don't want any classes to overlap. You don't want the same value to be counted in more than one class, or for there to be any doubt where it's counted. So the classes should be mutually exclusive, but there shouldn't be any gaps between classes. Where one class ends, the next class should begin right at the next number. So they should be continuous with no gaps between them. They should be exhaustive. So every data point should fall into one of the classes, and they should all be equal in width. So here's another example of a bad or incorrectly constructed frequency distribution. It breaks one of those rules that I was just talking about. Can you see which one? Now, the fact that we have a frequency of 0, that's not a problem. That's not the reason it's a bad frequency distribution. It is possible that you have a class with a frequency of 0. If you didn't have any data values that were anywhere from 33 to 38, well, then that class has a frequency of 0, but we still want to include it. So it's a little more subtle. You have to do a little maybe calculation or counting. 27, 28, 29, 30, 31, 32. That's a class with a width of 6. 33, 34, 35, 36, 37, 38, also width 6. 39 to 44, that includes 39, 40, 41, 42, 43, 44, also width 6. 45, 46, 47, 48, 49, uh-oh, that only has a width of 5. So there the problem is that the classes are not all the same width. What about this example? Can you see what's wrong here? This one should stand out a lot. Here, the classes overlap. The first class ends with 9, but the second class begins with 9. So if one of the data values is a 9, does it get counted in the first class or in the second class? Or does it get counted twice? That's not something we want to happen. So we don't want the classes to overlap. And also, I'm not sure they're all the same width, but the thing that really sticks out to me is that they overlap. And so, bad frequency distribution. Bad frequency distribution. And what about this example? What's wrong with it? Again, you can't tell anything from looking at the frequencies. We just got to assume that those are the correct numbers based on the original data. Whatever those numbers were, there were 3 of them that were in this class and 7 of them in this class. So look at the class limits. There's something wrong there. You see it? There's a gap between the second and third classes. The second one ends with 132, but the third one starts with 138. So what happened to the numbers in between, like 133 to 137? That should be listed. Even if there weren't any numbers that were somewhere from 133 to 137, you should still list the class, even if it has a frequency of 0. So here the problem is the classes are not continuous.